Hi, I'm James Powell. This is What's New in Python 3. We're at PyData San Francisco. It's Friday, August 12th, 2016. See, that's very helpful because people need to actually figure out when that video was taken, especially for something as timely as this topic. Now, one thing I also like to do with my talks is to maybe warm up the crowd a little bit by just saying, hi, everyone, I'm James. Hey, very good. So, and that's also a key, it just also kind of gives me a clue for who's ever seen me speak before. Something I like to do at the beginning of all of my talks. And it's just a nice way to get you guys warmed up. So this talk is called What's New in Python 3. One thing that I would say characterizes a lot of the talks that I've given, and I think this is our 20th PyData event, so that means this is the 20th time I've presented at a PyData conference, is what I pitch as the idea weeks in advance of the event and what I actually present on stage never quite match up, because you think, oh, this would be a great idea. People really want to hear about that. Then when you're actually sitting and putting the slides together, you realize, well, I don't know if I'm the right person to present this, or it feels a little bit different. So when I was putting the slides together, I wanted to give you a very straightforward view of what's new in Python 3. That said, as I began to think more about the topic and think more about what it means to give a tutorial rather than a talk, I thought what would be very useful would be to show you how you could actually determine that yourselves and how you could give a presentation like this. One of the disclaimers in my talk is that I am not a Python core developer. I'm not directly involved in the production of Python 3. I'm a Python 3 user. I'm very familiar with the CPython codebase. I work with two CPython 3 core developers, and I consulted them when putting together this presentation, but I'm an outsider to this process. In many ways, many of you are outsiders to a lot of the tools that you'll see presented at this event. But that doesn't mean that you're not able to participate in this event by giving a talk, by sharing with other people what you've learned about these projects and these tools. One thing about Python 3, or rather one thing about these kind of talks, is that they're actually pretty easy to put together because you can refer to material that's online, and I'll show you just some steps for how I actually put this together without having to reference other people's material. There are, for this topic or for many others, a lot of presentations about what's new in Python 3, what's new in Python 3.4, 3.5, specific topics or laser-focused versions of what's new in async I/O in Python 3.5 or what's new in async I/O in Python 3.6. But it's actually pretty easy to put together a talk like this, and I would tell you the developers of these projects actually like it when other people present their work. So some of you in the audience might be heavy users of pandas, and there are a lot of recent changes to pandas, a lot of improvements, and you might say, well, I really get a lot of value out of using these improvements in pandas. I'd like to give a talk, but I'm not a pandas core developer. I don't want Wes to get angry at me for going up on stage and maybe slightly misspeaking. In my experience, and from having met the core developers for all the tools that you'll see at this event, they actually like that, and they're more than happy to see other people present this, and they're more than happy to help you out if you email them or if you get in contact with the people at NumFocus. We'd be more than happy to connect you to core developers if you want to give a talk like this. But that's one common thread that I wanted to inject that's not actually in the materials itself, but something that I wanted to keep in the forefront of the talk. How would you actually give a talk like this? And that's what I consider to be the core of the tutorial content for this. Because the rest of it is more or less just a feature parade. I'm going to show you a lot of features in Python 2, or rather a lot of features in Python 3 that are new, and we'll go through them at a leisurely pace. We might skip over a couple of them, but I think what's more important is how would you actually be able to keep track of this? How would you actually be able to give a talk like this? And also, one thing that will be very valuable, I think, to get out of this tutorial would be to have more of you in this, see, the camera can't see you, so this humongous, enthusiastic, frankly quite beautiful audience give more talks like this at future PyData events. So let's get started. I want to start with a very simple survey. How many of you are still using Python 2? So almost everybody raised their hands. How many of you are still using Python 2 by choice? 2 or 3 or 4 people raise their hands. So just to drill down on that, of the 4 people who raise their hands, how many of you are using Python 2 by choice because there's some library that you need to use that's not supported in Python 3? How many of you are using it because you just think Python 3 is going in absolutely the wrong direction? How many of you are using it just because you haven't had a chance to look into what's new in Python 3? So there seem to be probably many other reasons for why people are still using Python 2 by choice. But I think what we can see is there's a strong desire for people to use Python 3, although it may not match up with what they're actually using in practice. Who here is using Python 3? Who here is using Python 3 for work? So that was about a fifth of the crowd raised their hand, and 1 or 2 people raised their hand for they're actually using Python 3 for the work. So I presume that the rest of you are using Python 3 in your own research or in your prototyping or off to the side. It's not part of your production process. Who's using a Python greater than 3.5? Who's using a Python greater than 3.4? So the same people who raised their hands before. So nobody here is using Python 3.5. Is anyone using Python 3.6? I'm probably the only person here who's used Python 3.6, and it's still a release candidate. It's not an officially released version yet, or at least it's not. It hasn't had its first proper release yet. But you can see that in a crowd of data scientists, the usage of some of these bleeding edge versions of Python, it's not going to be very common. Who here is using whatever version of Python was installed with Anaconda, and they just really didn't choose, they just installed, and that's whatever it's there? Quite a few people. And that's a very reasonable thing to see in an audience of scientific users, an audience of data scientists. You know, the choice between Python 2 or the choice between the various versions of Python 3 really isn't as pressing as a need to immediately focus on solving your business problems. And so you downloaded Anaconda, you installed Anaconda. Like many people, maybe the next time that you update what version of Python you'll use, you probably might not even update it via Conda. You might just wipe away your Anaconda install and reinstall Anaconda from whatever's on the Continuum website. Who here is using whatever Python was available via Anaconda when they first installed it, never updated it, it's still the same Anaconda install, never ran Conda update whatever, and they're just using whatever they had. That's just the tool that's in front of them. Okay, so nobody actually raised their hand. I would have expected, if we ignore some of the pointed wording here, I would have expected a couple of people to just be fairly ambivalent or even totally unconcerned with what version of Python they're using. Because for a lot of people, the version of Python is really not the most pressing thing. I got into an argument, or actually I had a back and forth very recently on Twitter where I was looking at some code that was written in Python for one of the poll aggregation websites, the Princeton election website, where they aggregate all the polls and they give a probability for each of the 2 candidates to win. And I had looked through the code because it was in Python, used matplotlib and NumPy, and I emailed the author and I said, I found a bug in your code. And the interesting thing about that is, and I think the San Francisco audience might like this, the reason that the author of this code had never run across the bug was because it was in a branch where he prints out information if the other candidate was leading in the polls, which had never happened. And so consistently, since he'd been publishing this information, one of the 2 candidates, and I won't say which one, but you can guess, was doing much better than the other. When I talked about that on Twitter, some people said, well, if you look at this code, it's not very good. It's like a lot of scientific code. It's just written, may have been written 10 years ago. It was written prior to the author learning what a context manager is. So it might have even been written prior to Python 2.4, 2.5. And it had never been updated. But the reality of the situation, if you're a scientific user, is you labor under different economics, and you're not being paid to use the latest and greatest. You understand that sometimes there are benefits to that, and we'll see some of the things you can do in Python 3.5 and 3.6. But you're not pressed in the same way that maybe a software developer is to adopt the latest and greatest. And I want to say that's okay. I think we need to have an understanding. At least there needs to be a more nuanced understanding between people who are on the software development side and people who are on the scientific side, that scientists maybe don't care that much about code quality, and that's okay. and software engineers do care a lot about code quality, and there's a reason for that, but there's not a contention there, or there doesn't have to be a contention there. Before we dive into what's new in Python 3, and I'm sure some of you are just squirming in your seats to actually figure out what's new in Python 3, I wanted to correct the title. And the reason I wanted to correct the title was the title here is what's new in Python 3. Except Python 3 was released in 2008. That was about 2,809 days ago, or 2,809 days ago when I updated this notebook last night. So we're talking about 10 years ago. We're coming up, in 2 years we'll come up on the 10th anniversary of Python 3. So I thought it would be kind of silly for me to come up here and tell you what's new in Python 3, even though a lot of you are using Python 2, because you've had about 10 years of time to see other people give that presentation. And I want to give you something that you might not have seen before. But in the same vein, if I were to talk about what's new in Python 3.5, Python 3.5 was released in September last year. So almost 365 days ago, almost a full year ago. And so in the intervening year, you might have seen other presentations about what's new in Python 3.5. In fact, I can point you in the direction of two good presentations. If you look up Aaron Muir, he's one of the core contributors to SymPy. He has a very nice slide deck online about what you're missing out in Python 3. And there was a talk last year at PyData Seattle given by one of the speakers who will be at this event as well, Steve Dower, about upcoming changes in Python 3. And I believe this was just very shortly after the release, either very shortly before or very shortly after the official release of Python 3.5. So if I wanted to correct the title, I might say this is what's new in Python 3.5 and 3.6. Except I have to put a maybe there, because the approach that I'm going to take to show you what's new in Python 3.5 and 3.6 is going to cover some changes that are actually still speculative. Python 3.6 is still in the process of being released, and some of the changes that are slated for that are still speculative. When we talk about the PEP process, you'll see that it's possible for a PEP to be accepted and then later rejected. And so some of the changes we look at aren't final. Even things that are final in the Python language can be removed later on. Things like tuple unpacking in parameter lists got removed from Python 2 to Python 3. Features can be removed. So what I'll show you is a view of what's in Python 3 and 3.5 and 3.6, but not necessarily everything that's there. There is a more important question than the question posed in the title. And the most important question, I think, is how do I keep up to date with changes in Python 3? The answer I'll give you may not be as easily generalizable to all the many different things you have to keep up with. But let's since we have a lot of time, it's a long session, and I'd like to get a lot of feedback from you. How many of you update the packages that you're using, whether it's something as big as Python or as small as one of the small add-ins that you have, maybe something built on top of NumPy or Pandas? How many of you actually update any of the packages that you use in your work environment on more than a yearly basis? Only a couple. How many of you really haven't ever bothered to update? I mean, you had a deployment environment, and you just stuck with that from when it was delivered to you, and you just keep using it. And there's no real... So that's a couple of people. How many of you update pretty religiously? You see, there's a new version of Pandas. I got to get on that. Almost nobody. Only a couple of people in the back. And this is also not too uncommon. Now, one of the reasons why that is, I think, can help us in this session. So, how many of you aren't updating? Because a lot of you are not updating very regularly. That, or you're already a little tired, so your hands are kind of lagging. But how many of you haven't updated because there's just too much going on? You have to follow all of the changes in the actual field where you work, and then you have to follow all these changes at the Python level, at the package level, at the operating system level. And after a while, you say, well, I'm running it out of hours in the day to understand what the latest and greatest thing is. And in many cases, that's distracting me from what I'm actually being paid to do. Come on, I phrased that so that more of you should be raising your hands. It's not an uncommon situation to be in. And so the question is, how do you keep up to date? And it's not a very easy question to answer. and it's not necessarily something that can be generalizable. One important disclaimer for all of this talk and for the answer I'm going to give you is that I'm not a core developer. I'm not a core developer of Python 3 or any of the NumFocus projects. I work with people who are core developers of these projects. I asked them about this question and about certain topics here. And I want to tell you what they said, but I am relaying their information. They told me there are a couple of different ways. One of the ways is to follow Python Dev. So some of you may know that there's a mailing list called Python Dev, and there's a mailing list called Python Ideas. And if you follow those mailing lists, you'll see most of the public conversation around changes to Python 3. Python 3 is a very large, the Python 3 core developers is a fairly large community of people who've known each other and have been working together very closely for a long period of time. So there are conversations that do not occur on the mailing list. There are small sprints or discussions that occur off list that are then brought onto the mailing list for discussion. But the mailing list is actually a pretty good resource for trying to see the entire, seeing the best snapshot of the public decision-making process. It is definitely true that at PyCon, a couple of core developers might corner Guido in a room and say, this is a change that we want, and they might have a discussion right there and make a decision right there without that being something that's on the mailing list. But for the most part, a lot of the major changes, or a majority of the major changes you'll see, are on the mailing list. The volume of the mailing list is pretty big. So if I open this link, you'll see, oh, I'm not connected to Wi-Fi, but the volume of the mailing list is pretty large. And what I have found is oftentimes I get the emails and I delete them the moment they hit my inbox, just because I don't have the time to read through a lot of bickering and back and forth about oftentimes what are very minor changes. Unfortunately, as with all mailing lists and all public discussions, there isn't a nice scaling or calibration between the importance of the topic and how much people talk about it. So sometimes people talk a lot about things which aren't very important, and then sometimes very, very important and very meaningful changes only get a little bit of discussion. So it's difficult to follow along. When I asked the core developers that I know and that I work with about this topic, how do you keep up to date? They all responded, follow the mailing list. And I said, well, what if you're a normal human being? And they said, well, okay, there's other approaches. So don't expect to be following this if you're a normal human being. It's a lot of traffic. The value of the mailing list is sometimes decisions are made and you might wonder why. You might say, well, this doesn't quite work, or I'm not sure what the motivation was. And the mailing list can sometimes give you some view into the history of why changes were made and some of the back and forth. There are actually two mailing lists. There's Python Dev and Python Ideas. Strictly, Python Ideas is supposed to be the mailing list where you come up with an idea, so something prior to the pet process. Now you can think that, and it's very important in the Python community to be very open to outsiders proposing ideas, even if maybe these are ideas that you've seen before or considered already. Python Ideas has a worse signal-to-noise ratio than Python Dev, just because it is the starting point for a lot of ideas. And as we know, a lot of these ideas aren't going to pan out. So if you follow both Python Dev and Python Ideas, you're going to have a lot of daily reading to do just to keep up to date. So I think it's a good reference once you want to understand a change better, but I don't think it's a way that you can actually keep up to date, unless your job is to be a Python expert at your organization. But if you're a data scientist or some kind of research scientist, there's just not a lot of value in spending your time there. Another thing that you can do is watch the bug tracker. The core contributors to some of the core libraries actually pretty religiously watch the bug tracker, especially for bugs that are relevant to them. So the Python bug tracker is public, and let me get online because I want to show you, I'll later show you one or two things from the bug tracker. And a lot of the discussion around features or fixes occurs in the bug tracker. So let me open this up and I'll show you. And let me see if I can even find, one that recently got a little bit of, I'll look through my name. Okay, so that would be, it's my name on it. I don't actually follow this very closely. Um,
James, can you make your font?
yeah, give me 1 second to, and what was it, dotted. So one thing that I had added along, yep, here it is, test list syntax. This is one thing that I had suggested for a decorator in Python. You can't have anything but what's called a dotted name. So actually, I'll do Python 3. So you can't do, you can do, if you have some function like this, you can do this, right, as a decorator. But you can't do, and you can do this, x.y, but you can't do x.y. It's not generalized. You can't put any expression behind the @ sign. And the reason for that is they just specifically disallowed it. So I put together a little, just as part of a presentation I was giving, I wanted to show people how to report bugs on Python. So as part of the presentation, I said, well, you know, here's my bug report. I have a patch. Here's some information. I went through the mailing list to figure out why that change was made. And there was some discussion, and some people actually really liked it. And you can see this was in 2013. And then very recently, somebody wanted to do something with this in 2016. And you can see, you know, there's some suggestion of this is very useful. And then Guido comes back and says, you know, I don't think so. And then the person comes back and says, no, this is actually very useful for my library. And then there's a little bit of back and forth. And in the end, it gets closed because Guido says, well, I don't see any real-world examples. This is an example of what happens on the bug tracker list. People have some suggestions that might actually be changes to the language, but they first say, well, this doesn't work, or this syntax isn't available, or I wish I could get this kind of behavior. And there'll be some of that public discussion mixed between the mailing list and between the bug tracker. And you can watch posts so that if there's updates to them, you'll see them. So the only reason I knew there was an update to this is I got an email. But it's still a lot of volume for not a lot of benefit. That's another possibility. One great thing that you could do is attend more PyData conferences. So I encouraged all of you to consider giving a talk at a PyData conference. One thing that you might not know about PyData conferences is a lot of people who you might consider to be accomplished and capable speakers got their start speaking at PyData. I don't know if I would be included in that or not, but I did get my start speaking at PyData conferences. We very much like to feature at these conferences people who have never given talks before as an opportunity for people for up-and-coming speakers to kind of get in front of an audience. And the easiest way to give your very first talk is to talk about something like what's new in pandas, because that information is all online. You can't really mess it up that much. You can speak to the core developers of the tool, and they'll give you some feedback. And you can do something that will be valuable for you, because learning what's new in pandas is going to be valuable for you in your daily work and also be valuable to the audience. So that's another way that you can keep up to date. You could check the what's news essays. So every time there's a release of Python, there's one of these what's new essays. And they detail all the changes. This is probably one of the best ways for you to keep up to date very broadly in what's happening in Python. Just because one of these is released only with each major Python version, so you're looking at one of these essays every 6 months, every year or so. And they're pretty comprehensive. They don't detail all the code changes to Python. So oftentimes there are very, very impactful code changes that are happening just at the CPython level that might not be covered by this. This is mostly things which Python users might run into. So if you manage some C extensions or you're a project author yourself, this may not go deeply enough to cover all the things that you care about. But for most people, you can see it's a pretty good resource. Now, if you look at this, you'll see that one of the sections is other language changes. Oh, here we go. You can see there's new features, other language changes, new modules, improved modules. It's pretty well laid out for what you care about. And there's not a lot of content here, or there's not a lot of material that you have to keep up to date with, and it's not updated that frequently. So I think that's actually one of the best tools to use. It is not, however, the tool that I used when putting together the materials for this talk. The approach that I took is to follow the PEPs. All of the PEPs. So one thing that you might already know is that all changes to the Python language have to go through an enhancement process, through an actual process. PEP stands for Python Enhancement Proposal. And if you go to GitHub, you can see a repo with all of the enhancement proposals for Python historically. Now, you could start this repo and check for any changes. Very speculative changes won't be added to the list of PEPs. So that's one way to filter out things that are very speculative. This changes very rarely. So you can see, and where it changes, where people actually add PEPs is not a very common thing. So if you were looking at just core language changes, probably following the PEPs is one pretty good way to do it. And that's the way that I put together this talk. I looked through all the PEPs, and I tried to extract the PEPs that were valuable or useful for you. One thing that a PEP will not contain is changes that are not visible to, changes that are not immediately visible to a Python user. So for example, there's an environmental variable in Python 3.6 called PyMalloc or Python.Malloc. And you can set it to change what the memory allocator for Python is, either to use the internally defined Python memory allocator, PyMalloc, or to use a system memory allocator, malloc, and to add debugging information. There's no PEP for that change. It wasn't considered to be a language change. But for a lot of use cases, if you are running in a memory-constrained environment, as quite a few people are, that might actually be a very meaningful change and something for you to know about. At the same time, I'm trying to think of an example of certain other changes, like rewriting libraries. Famously, the decimal library was rewritten in Python 3 as a C extension to be 80% faster. So if you want arbitrary precision decimal arithmetic, you can use a decimal library, and it's much, much, much faster than the pure Python one that was written previously. That change wasn't ever made in a PEP because it didn't change any functionality, it didn't add any features. It was just rewriting something that already existed in a better fashion. So those kind of changes won't be visible in the PEPs, but they may still be very useful or very valuable for you to know about. The way to keep up to date with those is those what's changed essays. Usually they will indicate when modules have changed, when there are new modules. Additionally, if a module gained a new function, that won't be in a PEP, it's too small of a change. The PEPs are for very large changes, or generally for very impactful changes. I shy away from the word large because you'll see from some of these PEPs, some of these aren't that large in terms of what they do, but they do have an impact from a language perspective on the code that you write. Oh, let me bring that back up. So I started with the PEPs, and that was the approach that I took for putting this presentation together. So before we go through a bunch of PEPs, and if you're bored now, boy, when we go through the PEPs, I want to tell you about the PEP process. PEP 1 details the entire PEP process. So it details how you submit one, what information is required, what the process looks like. I want to outline a couple of important things from PEP 1. Notably, all language changes require a PEP, but not all the changes that you're interested in may come through the PEP process. Not all language changes are approved by Guido van Rossum. There is, in fact, a delegate process that's been in use for quite a few years now. What happens when a PEP is proposed, one of the core contributors is allowed to nominate him or herself as a delegate for the BDFL, a subject matter expert, an authority in that area. If that nomination is accepted, then that person is able to decide where that PEP goes. This happens a lot in areas where Guido himself might not have enough experience to be able to make a good judgment. So for example, there are packaging BDFL delegates. There's people who routinely help make decisions in terms of how Python is packaged. People who routinely help make decisions in terms of how things with security in Python work. Typically for language changes like features, Guido handles those himself, although when Guido himself proposes a PEP, he allowed somebody else to be nominated to decide because he wanted it to go through a reasonable process where he wasn't rubber stamping his own changes. He wanted to have real feedback. Additionally, when you look at the PEPs, there's generally three types of PEPs. There's standard track PEPs, informational PEPs, and procedural PEPs, process PEPs. The standard tracks PEP are what we're going to look at and what we care about. Those are generally new features or new implementations in Python. The informational PEPs are just kind of general guidelines. So we're all familiar with PEP 8. PEP 8 is an informational PEP. They're useful to keep. They're useful to keep track of just because these may detail best practices or may detail things which are important for you to know about, but they won't detail language changes. Lastly, there are process PEPs, and they tend to be about things which are outside of language design. So for example, I believe the move of Python from Mercurial to Git to GitHub was in a process PEP. And you can think that's also something that would be important to keep track of. Wouldn't be in the what's new essay, but wouldn't be in one of the other two types of PEPs. It'll be in a process PEP. The other important thing when you're looking at the PEPs is to understand, is this something that I should care about? Is this something I should look at? And the way to do that is to just understand how the PEP process works. Draft PEPs, or PEPs start off as drafts. Somebody writes up a draft and they say, this is an idea that I have. Those drafts can be deferred if somebody says, it's not quite the right time. If it's a horrible idea, it can be rejected outright. If it's a horrible idea and you don't want to be publicly shamed by having it rejected outright, you can withdraw it. If it's a decent enough idea, it will be accepted. But an accepted PEP isn't necessarily something that makes it into the language. An accepted PEP eventually becomes final. So the final PEPs are the things which you're guaranteed to have in the language unless there's some other PEP repealing it. An accepted PEP, however, can be later rejected. And so this is very important because some of the changes, some of the PEPs that we'll look at are things which are not yet in any code base of Python. They've been accepted. They will eventually be in Python 3.6, but the patches haven't been accepted into the trunk yet. And so it'll be a little bit difficult for me to show you examples just because I'd have to build a Python with all of the patches as well. So let's follow the PEPs. What we can do is we can start by just cloning the PEP repository. And if we clone the PEP repository, we can see the PEPs are just text files. They're just text files in a very specific format. And you can see there are approximately 410 PEPs that have ever been written. We want all of the ones that are relevant to Python 3 and to Python 3.6. So what we can do is we can just grep for those PEPs. And if we look through this, we can see these are all the PEPs that are relevant to Python 3.5 or 3.6. And there's quite a few of them. There's 42 of them that are relevant. Now, I'm only looking at ones which have a listed Python version and which have a status of accepted, draft, will have any of the statuses we looked at before. Of course, we really only care about the ones which are accepted, rejected, withdrawn, or final. So if we filter down to those, we can see it's a much smaller list. Some of them were deferred and some of them were withdrawn. And we don't really care about changes which people said, well, this is probably a bad idea, either to do now or to do ever. And in fact, we probably only care about the accepted PEPs and the final PEPs, things which are likely to make it into the language and things which are definitely going to be in the language. And we probably don't care about the rejected or the withdrawn PEPs. So this is what's remaining. This list is just the accepted and the final PEPs that are marked for Python 3 and 6. And in this list, I'll go through only a couple of them. So this is a list of all the PEPs that we could talk about. I'm going to skip a couple of them. These are the ones that I'm going to go through. PEP 448, well, you can see the list here. And we'll go through them right now. So PEP 448, additional unpacking generalizations. This is status final, so this will be in the language. This is for Python 3.5, so this is already available for a lot of you to use. Let's take a look at what that is. You may be familiar with the PEP 3132. PEP 3132 gave you extended iterable unpacking. I'll show you what that means. We can unpack things like, we can unpack any iterable with a simple assignment syntax by just having comma-separated variable names on the left-hand side and then the values on the right-hand side. But we had to match up the exact number. We had to structurally match up the exact number and structure on the left-hand side as the right-hand side. So for example, let's start a Python 2. Here's a Python 2 terminal. I can't do this because I have too few values on the right hand. I have too few values on the left-hand side, for the values on the right-hand side. And I can't do this. I have too many values on the left-hand side for the right-hand side. Extended iterable unpacking said, well, we can use the same star unpacking syntax in order to capture the case where maybe we don't know how many things there are on the right-hand side. And so what I can do in Python 3, and just in a stock Python 3, just the Python 3 that comes with my computer, I can now do x, y, z equals 1, 2, 3, 4, 5, 6. And all of these additional values will be captured in z as a list, and those two values will be captured. And it's actually a very flexible syntax, because you can see I can put that star anywhere. And so this means there's some value. I can do more sophisticated destructuring. This is some value, then any number of values, and then one tail value. So I can do something, if any of you are old Lisp programmers, this might start to look kind of like car and cutter, where I can get the head of a list and the rest of the list. We could do those kind of destructurings. One thing that we can't do, because it would be ambiguous, is put two stars there. It would be ambiguous to determine which of those two variables, x, or rather y or z, would take the remaining items. So that's a PEP that was already accepted. If you look at that PEP, which we'll do, we can see that it was actually marked as standards track for Python 3 in 2007. So that feature has been around for a very long time for you. The PEP that we're looking at right now adds more generalized unpacking capabilities. So let's go back to Python 2. In Python 2, we might have a function that takes any number of arguments. And we might just print out what those arguments are. And we can pass it arguments directly like this, or we could pass it unpacked arguments like that. But we can't do a double unpacking, and we can't pass it arguments like that and then an argument at the end. There's some syntax limitations that in Python 2, just to reduce ambiguity, and just because these weren't considered to be completely generalized. In Python 3.5, we can now generalize the use of the star and the use of the star for tuple and keyword unpacking, or for regular unpack, for sequence and keyword unpacking in any expression context. So the first thing that allows us to do is say we have a function here, f, that takes multiple arguments. We can now pass it many things to unpack, and it does what you expect. It first unpacks that 1, 2, 3 into positional arguments, then it unpacks that 4, 5, 6 into positional arguments. I can give it single positional arguments, and then I can unpack more stuff here. And you can see it does exactly what you intuit. That could be useful. That could definitely be useful. However, the purpose of this PEP is to really generalize the use of the star and the star. So in any expression context where it makes sense for you to unpack a sequence or unpack a keyword, you can now do that. So what I can also do is here I can create a tuple with 3 values, right? I might call this tuple x. I might want to create another tuple y that is the values of x plus some other values. And this is how I would have done this in Python 2. In Python 3, I could just say it's x unpacked plus a 4, 5, and a 6. There we go. So we can see the use of this star unpacking has been completely generalized. The unpacking is not quite as flexible. I don't know if any of you have played with JavaScript recently, but I think ES6 has some really fancy structure unpacking that works really nicely for that language. The destructuring in Python 3.5 is generalized, but it's not quite as flexible. It doesn't have all the features of that. But it's in the same vein. It's a very useful thing to do. You can make some, you can write some things a lot more tersely. Now, one of the motivations I see for this PEP was there was always this question of, I have 2 dictionaries. And how do I merge 2 dictionaries? How do I merge these? And some people would say, oh, create a new dictionary and then do x.update, or rather z.update of x and z.update of y, and you could merge them like that. Or other syntaxes that might be terser than this. You could do kv for kv in x dot items, y.items, you can do it like this. You could do something like that as well. But you can think with a generalized unpacking. Now you can just say, I want a dictionary, and I want a keyword unpack the values of x, and keyword unpack the values of y. And so you can now merge dictionaries very nicely with a very simple syntax. This is, I think, one of the, you can think that for normal tuple unpacking, one of the motivations for that is just the really nice and very concise format for swapping two variables. You could think that maybe this dictionary unpacking is its equivalent, this motivating feature. Now, what you can see from the examples on the screen is that you can use this in any expression context. So I can now create a list. If I have a list of values, I can create another list that's just those values unpacked and then some other values here. Any context in which it makes sense for me to unpack, I can now use that star unpacking or that star unpacking. Similarly, you can mix and match these to your heart's desire, but I think the idea should be fairly clear. So let's take a look at our next PEP. There's quite a few of these to go through. PEP 465. Now I wanted to, when choosing which PEPs to look at, I wanted to skip some of the PEPs that would take a very long time to look at and also wouldn't be that interesting for this audience. One of those PEPs was the type hinting. The type hinting is, I feel it's a very speculative PEP just because it outlines a syntax for tools that aren't quite using it yet. Type hinting, there aren't that many tools that are using the type hinting support just yet. So it's still in a fairly speculative place. I wanted to skip other PEPs that were probably already well known to you. This is one that might already be well known to you, but I think it's something very major, not for what it does, but for why it was introduced. So as you might know, in NumPy, we have two array objects. And if we multiply those two array objects, we're going to do an element-wise multiplication. So here, even though I'm trying to multiply x times an identity matrix, I get element-wise multiplication. And I should get x back out. But I don't. It just multiplies each value. Well, the reason for that is NumPy deals with arrays, not matrices. So it doesn't really know that you want to do a matrix multiplication operation. All of the arithmetic operations that it performs are assumed to be element-wise. Now, historically, the way around that was to explicitly tell NumPy that these are matrix types, which would then cause the multiplication operation to perform matrix multiplication. So you can see here, if I do that, you can see I multiplied x times an identity matrix and I got x back out. Except this becomes very clumsy because oftentimes you want to deal with NumPy arrays. You don't want to have to wrap them in this matrix type. And sometimes you want to do element-wise multiplication, and sometimes you want to do matrix multiplication. Other languages introduce sets of operators. So I believe in R you have dot, and then the operator by itself to distinguish between element-wise and not element-wise operations. I'm not sure if that's correct because I'm not much of an R programmer. In Python, it was identified that at least this was one area where things were getting kind of ugly. So in Python 3.5, a new operator was added, the commercial at, and that indicates matrix multiplication. Now, there are a couple of things I wanted to say. One, the at sign doesn't really mean matrix multiplication. The at sign means invoke a protocol called matmul. So the protocol very heavily suggests matrix multiplication. That said, what actually does the matrix multiplication is how this protocol was implemented in NumPy. What that means is, if you wanted to create any number of really horrible APIs using an at symbol, you're free to do that now. It's just a new operator that you're able to overload. In addition to plus, minus, divide, you now have the at operator, which I'm sure you can already think of some terrible email-related or who knows what, Twitter-related. You could do like tweet at somebody and maybe that sends off a tweet. Who knows? You do some really terrible things with this operator. The reason I wanted to repeat, or the reason I wanted to bring this operator to your attention again, is that I think it marks a very meaningful change in the development of the Python language. Everybody here is a data scientist. And y'all represent, in my estimation, a good probably third to greater than third of the Python community. The Python community has, if you wanted to just very easily divide it into three groups, there are all the web programmers out there using tools like Django and Flask. There are all the system programmers out there who are writing tools like apt or shuffling data from one side of an organization to another or building automation or testing frameworks. And then there's the data science people. Historically, if you look at a conference like PyCon that was held a couple months back in Portland, almost all the talks were people talking about system stuff or people talking about web stuff. In the last 2 years, owing to some hard work by some of the volunteers from the Project Jupyter organization, more talks on data science were included in PyCon. And I think this past PyCon was 1/3 data science talks. What this means is the core developers for the Python community, none of whom come from a data science background, are beginning to better understand that there are a lot of users out there who are scientific users who want this language for scientific use, and they're beginning to understand that in order for them to make these users happy, they need to recognize the needs of those users. I see this PEP, if I wanted to, it's a little facile, but I would say that I see this PEP as a symbolic move to say, okay, we're recognizing the needs of data science users, of scientific users, where previously we had mostly been focusing on the needs of systems users and web programming users. And I think that we're going to see many more PEPs and many more changes to the language in the future that make it easier for you to use data science tools than we saw in past. And so that's why I wanted to bring up this PEP. I think it's something that's very meaningful. Because if you ever have a chance to see Guido at PyCon and talk to him, you'll see he really doesn't know a lot about what we do here at a PyData event. We actually invited him to speak at this event, but he had a family trip. But he was actually very interested in speaking at this event. And I think one of the things that he could have brought to you is just talking about how a lot of the core developers don't come from the same background that all of you come from. They don't have that exposure to the needs of scientific code, whether in research or in industry, and how they've had to integrate that into how the Python community works, how the core development community works. Let's move on. And let's talk about PEP 485, a function for testing approximate equality. This is one thing which you might say, I shouldn't editorialize too much for all these PEPs. One thing that I think you'll see in the PEP process is that one clear focus of the developers of the Python language is to make it a friendly language for newbies to use. And so I think that 485, I would see that more as a tool to make it clear and obvious for people who aren't professional programmers to use Python. I'll show you what it does, and then I'll tell you why. We know that if we take two numbers, 11 and 22, that's equal to, when we sum them, that's equal to 33. But if we do 1.1 plus 2.2, it's not equal to 3.3. We might wonder why that is. And we might actually say, okay, well, if we look at 1.1 plus 2.2, this is done in IEEE 754 floating point mathematics. There's some imprecision, and that's the result that we get. In fact, if we do 0.1 plus 0.2, and we take the result, and we paste it into our location bar and put a .com at the end, you get a really neat website that tells you how floating point math is handled in all different languages and tells you a little bit about why this happens. This leads to, you can think for a lot of people who aren't long-time programmers, this can lead to some consternation because they might see an expression, they might say, well, I'm adding these two numbers or I'm comparing these two floating point numbers and they should compare as equal. But there's a problem because maybe one of the numbers is supposed to be 0, but it's actually 1 times 10 to the negative 16th. It's very close to, but not exactly 0. In fact, this happens more often than you'd like with even core libraries. So if I do from math import sine and do the sine of pi, the sine of pi is not 0 in Python. It's just very close to 0. And so if I were some scientific user who didn't have in the forefront of my mind, oh, this is IEEE 754 and there's floating, there's error, I might write code like that and it wouldn't do what I expect. So what the Python developers, or what the PEP does, is it adds an extra function to the math module called isClose. so that you can determine if two numbers are close. So here you can see is 1.1 plus 2.2 close to 3.3. It's supposed to be, and this is something that you would have done yourself just by saying 1.1 plus 2.2, absolute value of this minus this, less than something. You would have done this threshold checking yourself, but it gives you, a standardized single place to do that threshold checking. That should be something obvious for newbies. One motivation that you'll see in the PEP process for things being accepted is that in many cases, the Python core developers look at how code is used in the wild. So they'll do Google searches. There used to be a really nice part of the Google website where you could do searches through code bases. But they'll try and do searches through GitHub or through publicly available code for patterns and see if people are using patterns that they're trying to do better. The other thing they'll do is they'll Google for how do I do X, Y, Z in Python? And they'll see what Stack Overflow or what one of the question answer sites suggests. And sometimes those answers aren't very good. And if those answers aren't very good or aren't very obvious, they'll say, well, this is something that needs to be fixed about the language. Because you can imagine, for all of us professional, capable, super sophisticated Python users, how many users out there are using it just as a tool and they run into a problem and the first thing they're going to do is Google for it, look on Stack Overflow, and they need Stack Overflow, and they need the obvious answer to be, they need the answer to be obvious and clear. And so by changing the language, they can motivate that better. So this is one example, I think, of that. Is close, of course, gives you the ability to do with a relative tolerance. So here we can see is 90 close to 90.1 with a relative tolerance of 0, but an absolute tolerance of 0.1. So this says is 90 within 0.1 of 90.1, and that's true. And here you can also do it with a relative tolerance. Is 90 within 10% of 95, and that's true. So you can do both relative and absolute threshold checking with just one function. And so if anybody asks you that question, or if you were to Google for that question, hopefully the top answer on Stack Overflow would say, just use this function and eliminate a lot of back and forth, a lot of consternation that people who aren't intimately familiar with the nuances of floating point arithmetic might run into. Let's take a look at PEP 487, simpler customization of class creation. This one is really obscure. So this is actually an accepted PEP. So you can see this one is status final. This PEP was actually, there were two PEPs talking about simplifying class customization. One of them was withdrawn, PEP 422. And it was withdrawn because the PEP that I'm about to show you does a better job of the topic that we're looking at. So, we might use some tool from some library, like some class. So imagine there's some library and it has a class A, and there's a class B, and unknown to us, there's some need to customize the creation of those classes. There's some need for a meta class. And so A has a meta class and B has a meta class. And that's not necessarily a detail that we would know about or care about. It might not even be visible in the documentation for these two libraries. You might just see class A and class B, and the meta class might be considered to be part of the implementation, and so not part of the public API. What you're going to do is you might want to have a class C that inherits from both A and B. And unfortunately, there's really no nice mechanism for doing this while remaining ignorant of A and B having meta classes. Because if you try and inherit from A and B, and notice A and B are not fancy classes. They don't do anything. And their meta classes don't really do anything either, except print out a message to the screen. But when you try and inherit from A and B, you run into a meta class conflict. The reason for that is, in constructing the C class, we have to determine what meta class is being used. We look through all the base classes. All of the base classes, you need the most derived meta class, and if the base classes, meta classes, derive from different hierarchies, there's no way to reconcile that. You can't tell which of the two meta classes to use. Consider that a meta class essentially is any code that can do anything that you want to customize the creation of a class within some fairly limited constraints, or some fairly, actually not that limited constraints, but within some constraints. And so there's no way to generalize the merging of two meta classes or to decide which of those two meta classes is more senior to the other than some nominal mechanism for indicating that one is more derived than the other. More fundamentally, we want to write our own subclasses, and we want to subclass things in libraries, and library authors want to use meta classes to do their work. It's a nice way to implement a lot of the functionality they want to provide to us. But they don't want us to have to bear the knowledge of how that implementation works. And so this is a giant wart. What was identified is that before I show you the change, most of the cases where people were using metaclasses fell into about 3 categories. The first one was you create a subclass and you do a couple things to the methods of that subclass. The second one was you need to know the exact order in which the attributes in the subclass were defined. So think for an enum, if you wanted to create an enum and you wanted to automatically number that, you automatically number the elements for the constants. You want to have numerical value equal to the symbolic value. And you wanted to have that numbering work automatically, you'd have to know the exact ordering. But that's not available because the meta class gets a dictionary of all the class contents. And since dictionaries aren't ordered, you have no way to know the actual ordering of the things inside the meta class. This is why in Python 3.4, I believe, they added prepare as a underscore method to meta classes so that you can tell your meta class what the dictionary subclasses should use for building the contents of the class. And that's how they were able to implement the enumerated type. That said, I said there were 3 things they have to do. The third one is calling specific methods on attributes of the class. So I'll show you what this PEP does. What it does is it tries to create a simpler set of protocols in CPython for changing how classes work that are less flexible than meta classes, maybe more understandable to a general audience, more tractable, and also allow for easier merging when you want to do multiple inheritance with 2 classes that have this functionality enabled. So let's talk about the first thing. So one thing that people might want to do is they want to control class creation. So for example, one example I can give you is I worked in an environment once where we were using unit test. And unit test has a setup and a teardown method. And in the setup method, we all had to call a very specific method in that setup method in order to initialize a testing database. And if you didn't call that method, your unit test wouldn't work. There were 2 proposed solutions to go through our many thousands of lines of unit tests to make sure that happened. One of them was to just grep for cases where people didn't write the unit test correctly and send them an email. And to have a job that sat behind the scenes grepping every day and then sending nasty emails to people. The other one that I proposed was you write a 10-line meta class so that every time you create a unit test, when that unit test class is created, it automatically does the behavior that you want. So you're guaranteed that all the methods in the setup method would definitely be called. Very easy to do with a very simple meta class. What that meta class does is it says all subclasses of this type have a certain requirement. One easy way to think about meta classes is it's a way for you to have a guarantee enforced from a base class down to a subclass, as opposed to the other way around. So for a base class to say, if you're going to derive from me, you have to do these things. And the reason you have to do these things is because when you're created, I'll have a hook into your creation code to force you to do certain things. That hook was added explicitly as init subclass. So here we have a base class and a derived class. And when we run this code in our Python 3.6, so this is only a Python 3.6 feature, so I have to bring up a Python 3.6 Python interpreter, which I source compiled. One thing that I wanted to do for you is show you how to install Python 3.6 in Anaconda. There is a Conda channel that provides Python 3.6, but I couldn't get it to install, so I had to build everything from source. But what you can see is I have a base class and a derived class. And if I stick this in my Python interpreter here, let me do the base class first. Every time I try to create a derived class from this, it'll call this special code. It'll say somebody's trying to derive from me. We need to do this in, actually, we can't do this in Python 3.6. This is the Python 3.6 that's on the Python website. It's not, the code's not even there yet. The code's in only the Git repository. So I have to do that one more time. Here we go. So here we go. So every time I try and create a derived class, you can see it's calling that callback. And that callback allows you to then customize the creation of this class. So you can think meta classes are used for things like abstract-based classes, enforcing that abstract methods are implemented. You could use that with an init subclass. Because an init subclass has the ability to call a super method, then you can think that the danger in this kind of meta class conflict is eliminated. It's no more dangerous to use an init subclass as it is to create your own init. If you forget to call super, then that's your own fault. And using the linearization, the method called linearization, super will call the init subclasses in the right order. So that's one of the pieces. The next piece, so that's an example. The next piece is a function called setName. So when you create a class, let me create a data item, and I'll define setName, and I'll just print out whoops. And it doesn't have to return anything. So now when I create a class, if I have any of these here in the class, like consider this is a very common pattern for descriptors, that setName will be called. So what you can do is you can trigger code on the descriptors that are created for your classes. This is another common thing that's done. So this isn't on every instantiation of the class. It's on, or rather every instantiation of an instance of the class. It's on the instantiation of the class object, the type object itself. So it's a callback that gives you a hook into that. So that's what that does. And then lastly, the last part of giving you the definition order is provided by a separate PEP, PEP 520. What PEP 520 does is it gives you an underscore item on a class that gives you the original order in which things were defined. So I'll show you what the current case is. The current case is that if I create a class foo, and I have A, B, and C, if I look at the dict for foo, or if I look at the dir of foo, I get the elements, but I don't necessarily get them in any specific order. Coincidentally, these are in the order A, B, C, but really there's no ordering guarantee here. So I wouldn't know the order in which these were laid out. It was considered that, and this is a fairly major change to Python, although it doesn't affect a lot of user code, but it was thought that the order in which you define things in a class body in Python is very much intentional, and so retaining that order is very important, and so they added definition order to get the actual order in which things were defined. This greatly simplifies the creation of things like enumerated types. So that's that change. This is a very big change that I want to really quickly gloss over with two examples. PEP 492, coroutines with async and await syntax. So who here is using some kind of async IO library, whether async IO itself or one of the user-supported versions? Not a lot of people. And it's not too uncommon. Most scientific users are, if we were to talk about the performance approaches that most scientific users use, the first one is not using pure Python, using NumPy. The second one would be using C extensions. The third one would be using Python, or maybe Python and then C extensions. The fourth one might be looking into tools like Dask or some of the large frameworks that you'll see presented at this event. And it's fairly rare that for scientific tasks you'll look at things like async IO, just because for many of your problems they're CPU bound and not IO bound. But you can imagine some problems that you're dealing with are IO bound. And in the world of web programmers and system programmers, a lot of their problems are IO bound. And so because they're not waiting for CPU cycles, they're just waiting for network requests to respond, it's very helpful for them to have good syntax to handle asynchronous IO. What that means is, and I'll show you two examples from two blogs, and the references, the links are at the top of the examples. This is via a really nice blog post by Brett Cannon, via a tutorial on async IO. Here we have a fairly simple example of a countdown, a coroutine. What it does is it prints out something, and then it sleeps for 1 second. When it sleeps, because this generator has the ability to yield execution back to the caller, it yields execution back to the caller, which in this case is the event loop. So you have some event loop that can go through all the processes and say, are you ready to do something? If you are, run. Otherwise, go to the next one. If you are, run, and so on. And so you can have multiple tasks running simultaneously, only waking up when they're ready to do something, namely when they're ready because some operating system mechanism like epoll has said there's I/O that's ready to be read off of a socket or something like that. And so without using threading, which has problems related to the GIL, or multiprocessing, which has problems related to the ability to share data, we can now write code that, at least for I/O-bound problems, doesn't block on slow I/O operations. One of the most exciting things to come out of this, I think, is there's a new Postgres library that uses the async I/O tools that is very fast. It's fairly new, but it's very fast, it's very Pythonic, and it's something that I've personally been very excited to use in my day-to-day work. So this is what it used to look like. So this is not what the PEP does. This is async I/O when it came out in Python 3.4. A lot of patterns were seen in the usage of async I/O, where we were using decorators like this to create these coroutine objects, to take normal generators and to indicate that they were actually used for async I/O. And so specific syntax was introduced in Python 3.5 in order to make this easier. And so this is where you see this async def, and this await. I really wish I had more time to go into this in greater depth. There should be an async I/O and async await talk. If not at this event, we'll do something in the BOF room, because I think it's a topic that's worth putting a solid hour of information to. So if that's something that you're interested in, please let me know, and we'll set up a BOF session tomorrow with one of the developers of this tool, actually with one of the core developers, and we'll go through this in a lot of depth. So I apologize for glossing over that. PEP 495. One thing about this PEP that you can see is that PEPs aren't always that major. PEP 495 merely adds a single attribute to datetime objects called .fold to represent when two datetime objects represent the same actual time, when two distinct times represent the same actual time. So think daylight savings. You know, on March 13th, you roll your clock back at 2 a.m. or you roll it forward at 2 a.m. And so you have two physical times that represent the same time. It's a folded time. All it does is it adds a single attribute to the datetime object that's set to 0 or 1 on whether this is a folded time. So PEPs aren't always big major things. Sometimes they can be fairly small things. But in a case like this, it's something that required a lot of discussion and a lot of deliberation and had some real effects for people who are doing things, who are getting into the nitty-gritty of datetime library. PEP 498. This one actually ended up being much more controversial than you'd think. So, when I started with Python, we had this style of doing string interpolation. We used these kind of printf style percent formats. So here I'm printing out the number 10 as a floating point number with 2 decimal points of precision. And then the so-called advanced string formatting came along. So we have these curly braces techniques, and it's the technique that I use. And it has some nice things where you can pass rich objects and then create your own set of formatting parameters so that you can, instead of passing strings around in your code, pass rich objects and have the templates decide what parts of the rich objects to extract. So here you can see I'm printing out the date, but I'm not passing the parts of the date. I'm not calling some string ftime function. I'm passing the date object itself, and the template's deciding what parts of the date object to use, which is very useful because the template knows more about the visual representation of this information than the code that's being inserted into the template. One other thing that I didn't add here is in the string module, there's a template function. I don't know if anybody uses that. I've never used that, and I haven't really seen it used, so I skipped it. What this PEP does is it identifies that oftentimes we want to do something that looks like this. We want to create a string using some local variables. And there's some limitations to this. First, to do it this way is kind of ugly. We know there's this function locals that gives us a dictionary of all our local variables, and we could keyword unpack it, and we could use named arguments in our advanced string formatting. But this is a little ugly to do, and it's a little bit clumsy. And there are some real limitations to this approach, because locals will not contain variables that exist only in the closure. So you have to end up forcing that to be recognized as a local variable, and it gets kind of clumsy. For what is a very simple thing that people want. They want to be able to do a kind of string formatting that we're familiar with from using Bash or Ruby or I think even Perl. A lot of other languages that make this available. You want to create a string and you want to have placeholders for variable names and you want it to just interpolate that automatically. So f-strings were added to Python. An f-string is just a string where inside the curly braces you have any arbitrary expression. This is actually kind of interesting because it can be any arbitrary expression outside of, so any expression, so no syntax, but actually I'm kind of curious what you can do. So obviously, where this is intended to be used is like this. Yeah, it gave me my x and y. But there's no reason you can't do this, right? I wonder if you can do this. Oh, let me do this. I wonder if you can put a string. I don't think you can. Oh, that's really horrible. So now your strings can contain any arbitrary executable code, including calling modules. So there are oftentimes unintended consequences for some of these PEPs. So now just be careful. Oh, and here's the neat thing. Let's figure out when's the. Let me show you something. But I wanted to, oh, I need to do it like this. So one important thing though is this evaluation is, or this is evaluated at, actually no. Yeah, this is evaluated at string creation time. So it's not going to be the case that you print out a string, and it's probably not going to be the case that you print out a string and somebody's added some executable to that code to that string and suddenly all hell breaks loose. Because the evaluation order of this, you still have string literals and you do have some expressions in them, but at the string evaluation time, whether that's in a nested scope or in the top level scope, is when the expression will be evaluated. So thankfully, you're not going to take some user input and suddenly that user input is going to call arbitrary functions on your code. That would be a nightmare. So there are some limitations to that. But that's what the f-string format is. And it's something that's been added. There has been a lot of discussion on the mailing list about other letters to put in front of strings, other types of ways to do string interpolation. But this is the only one that's made it through the PEP process so far. And you can see for simple uses like x and y, it's pretty good. Maybe for something like x2 plus 2, that might be useful. For putting arbitrary expressions inside of your string template, that may not be so useful. But you can think one thing that you can think. I don't want to say this is not that useful, or I don't want to disparage this feature, because you could say here I have some templated string, and maybe I want to do the length of the templated string to figure out, +3 to figure out some formatting to align it nicely, and I could do something like that. So let's, I don't know. So let's continue. PEP 506, adding a secrets module to the standard library. So when people need to do things with cryptographic secrets, they oftentimes will just Google for, how do I do such and such? How do I create a password? How do I create a token in Python 3? And Stack Overflow posts show many different approaches. A lot of the approaches that you'll find on Stack Overflow and blogs don't necessarily use the cryptographically secure primitives in the Python standard library. What I'll tell you is the Python standard library contains primitives that are safe for you to use in cryptographic applications. That said, it's not always obvious where they are or which ones they are. There is a random module, and the random module contains a lot of things. And it's not obvious, is this safe to use or not? There is a desire to add a new module in the standard library called secrets, which is an obvious place for things which are cryptographically strong. So that when somebody asks, how do I generate a random token and I want it to be cryptographically strong, or how do I compare 2 byte strings and I want it to be resistant to timing attacks, I want it to take exactly the same amount of time, irrespective of where they differ, the secrets module contains that. And so it's supposed to be just like in the case of the previous PEP, it's supposed to be something that's very obvious for people to direct, especially users who are not already experts in this field, to the right place to do it. So this module is intended to contain functions for creating session keys. It'll contain interfaces to the cryptographically secure parts of the random module. So a way to in a cryptographically secure fashion, randomly choose something, randomly derive sets of bits, randomly generate numbers from 0, on the opener from 0 up to some value, so basically a rand range from 0 up to some x, and to do things like timing attack resistant string comparison and byte comparison. Let's take a look at PEP 515. Maybe, so there's no code for this PEP, so I can't show this to you in practice. It hasn't been added to Python core, there's just patches. But this may be probably the only PEP that you might be really excited about using. If you have a number like this, I don't think any of you can tell me within about a second of time whether this is 12 million or 1.2 million. Now you can add underscores to separate the digits. That really, I think this is one of my favorite PEPs out of the whole list. This really helps. Steven, is there a question? Oh, 5 minutes. So you can see, PEPs don't always have to be big things, but they can actually really help you out. And this is something that could really, if you knew about this and you were able to use this in your Python version, you're using Python 3.6 and the code was available, this could really help you improve your code. And also, if you saw this as code, you might wonder what's going on here. And having just some very broad understanding of the PEP process and what PEPs are available, you might look at this and say, oh yeah, this is just this PEP. Bear in mind, I sound like I'm very knowledgeable just because I've actually prepared materials for this, and so I know the names of all the PEPs. I don't actually know the names of the PEPs outside of this presentation. I just know them because I put together these materials. So don't worry if you don't know that PEP 448 is. I was talking about it like a minute ago. I can't remember which one that was. So don't worry about that. Just be aware that these PEPs do exist and that there was some discussion, and then that is your resource for an official version or an official description of the motivation behind the problem, the solution, and discussions around the implementation. PEP 519 was adding a system path protocol. This is a very, very small PEP. In PEP 428, the pathlib module was added to Python. The idea was people are storing system paths as strings, but we want to have a rich object for storing these. So in Python 3, you can already do this. There's a module called pathlib. You can create rich path objects. You can use this debatably elegant syntax to concatenate paths. So here I'm creating a path to user and a path to lib. The thing is, all of the places you want to put a path, like an open function to open a file, they don't take rich objects. They take strings. And think about all the APIs that still take paths as string objects, not as rich objects. Well, that's one of the big barriers to using a rich path object. So a new protocol was added called fspath. And fspath is just another underscore function that you can define that gets called when a part of the standard library or part of some library that needs a path as a string needs to get a string equivalent. So what you can think is if you're creating your own path objects or you're using the pathlib, you can now use it safely with functions that need paths of strings or sequences of bytes. If the author of those has implemented this protocol, you can now use rich path objects. That's really all it is for. This is one of the last PEPs that I'm going to talk about, and it also shows you one more thing about the PEP process. It was the addition of math.tau. This is accepted. It's in Python 3.6, but the code is still in patch form, so I won't show it to you, but it doesn't do too much. Now, bug 12345 on the Python bug tracker was created by a very nice guy who we haven't yet gotten to speak at a PyData event, Nick Coughlin. And some of you may be familiar about the tau manifesto, the idea that if pi, looks like that, tau is just one of them, and a lot of formulas like, the surface area of a sphere are much simpler if you talk about not pi, but pi over 2. If you look at this bug track, and the reason I wanted to show you the bug tracker is that this is where a lot of the discussion of this happens. There are some people like Aaron Muir, the aforementioned core developer for SymPy, who says, it's cute, but nobody in the sciences really ever uses that. Nobody in mathematics really uses tau. It's not something that's very useful. And in fact, instead, we want something like, I think he wants Euler gamma added to the math module. And they say, no, don't. But this was added as a joke. This bug report was added as a joke by Nick in 2011. And some people took it seriously, some people were just kind of jokingly. And then very recently, I believe on Nick's birthday itself, Guido said, where does he say it? So right before the arguments against it, I'm just going to do this. So it got accepted. So in future builds of Python, you'll be able to use both Py and Tau. The argument for that, there's a very nice discussion of why this is not a good idea by Raymond, who may be at this event this weekend, where nobody does it. He's never seen this in production. Adding mysteriously named constants degrades the usability of it. I can survey the audiences at the upcoming SF PyData conference to see if any of the participants have any clue what this is about. And Guido says, great, I agree with your arguments. I agree with your
in a place where people might not need to get together to have a little bit of fun. Some of the pets that you might be familiar with, so pets always introduce pet every year. And this was, I think, originally started as something of a joke. It was added just to recognize sort of a long-standing core development. And so soon enough, we'll get to saying how it goes to. So that's what's in Python 3. A very, very quick overview. You can see all I did was build the pets. I can still look for you. You can put this presentation together yourself. You will be able to do a better job than I am. Hopefully, but in any case, I hope this gave you kind of a view of not only how to keep up to date with the technical Python, but also just a couple of things to watch out for in 10 years when all of you are actually using Python 3. Because by the way, Python 2 is no longer supported by Python. Thanks.